Good evening, everybody. This is Paige Godfrey. You're listening to my Intro to Astro course here at Slooh. Tonight I'm going to be talking to you about our solar neighborhood. Last week we talked about our nearest stellar neighbor, the star system Alpha Centauri, that is closest to our sun, at just a little over 4 light years away. And today I'm going to talk to you about our full neighborhood, what's really all the way around the sun, out to about 100 parsecs, and some of the objects that are in that neighborhood that we can't see them any further away than that because they're so faint. So I'm going to start with an image. Let me remove there we go. So this is an artist depiction we're looking at on the screen right now. If you're at slooh.com listening, I am screen sharing with you. Because then you can see some of the diagrams that I'm looking at, and you can see, I might pop over to Slooh because actually, so I thought our telescopes were going to be clouded out tonight, but it looks like they're online, so we might pop over there in a little bit and see what's going on. So if you follow me at slooh.com in the Space Situation Room, you can see what I'm looking at when I describe images to you. And so what we're looking at right now is an artist's conception of a brown dwarf solar system, is what I'm going to call it. So the brown dwarf is the host star in the center, the way our sun is, and around it is a disk of gas and dust that would be like a protoplanetary disk that would form planets. So this is just kind of a little teaser for what we're going to talk about tonight. And if you didn't get the teaser on Twitter, the faint objects that are in our solar neighborhood that are really interesting to me because they are too faint for us to see outside of this about 100-ish parsec area are brown dwarfs. So I think the first way we should start talking about this here is, how do we measure these distances? Like when I say something is close to our solar system or when I say something is super further away, how are we measuring this? Because we talk a lot about how when we look up at the night sky, we see everything in what looks to us like a 2D flat plane. This is how we have constellations. So constellations, the individual stars, are not actually lying next to each other. Some are very distant compared to others, but we lose that third dimension due to the limitations of our own eyes. And we call this the celestial sphere, where the objects that we can see in our night sky appear to all lie in the same plane. So how do we actually measure these distances? Well, when we talk about stars that are really, really far away, that's not what I'm referring to here when I'm going to talk about parallax in just a second. So right now I'm talking about measuring stars and brown dwarfs and things that are closer to our solar system because they have what we call a parallax. So a parallax is the apparent motion of an object compared to a more distant or fixed background when the location of the observer looking at this close object changes. So what's happening is, you can see in the image here that our Earth is orbiting our sun, right? And at one time of the year, we are on one side of the sun, and at the other time of the year, halfway around the year, we are halfway around the sun. So the two lines of sight here are one in July and one in January. And, we move through the orbit on the other months. When we're looking at a star that is closer to us, we're calling this the foreground star, and then these are the background stars. They're so far away that they don't appear to be moving in our night sky. If you think about while you're driving down a road, a car that is near you looks like it's moving, but a car that is really, really, really far away doesn't. Think of like a cruise ship out on the horizon in an ocean. It barely even looks like it's moving because it's so far away. Whereas a kid chasing the volleyball across the beach is zipping right by you. That's what we're looking at here. And so what happens when Earth orbits the sun, our vantage point changes. And so our lines of sight, when we're over here in July on the left-hand side of the sun, and we look at this foreground star, we see it along this axis. But when we orbit around the sun and we're over here in January and we look at the same foreground star, it appears to have a different axis. And so if you imagine this big orbit that Earth is sweeping out, and then you draw these lines of sight up through the foreground star, you can see that there would be another little tiny elliptical orbit, I almost said circular, but elliptical orbit, that the foreground star appears to make, even though it's not actually making that elliptical orbit. It's due to our elliptical orbital motion. So we call that a parallax. And so foreground stars, meaning ones that are close to our solar system, have a large parallax, whereas the background stars that are really far away don't have a large parallax at all. And actually, it's immeasurable in most cases, because if you were to pretend, I mean, this scale is not great to describe the background stars, but if you were to draw the line of sight to a star that's much further away, then this line of sight axis drastically goes up and this parallax angle gets much smaller. So this is how we can tell if a star is close to our solar system or really, really far away, if it has a measurable parallax. And then by measuring the parallax, we can do some math, and after that, we get the distance to the object. So it sounds kind of simple, but the math involved is actually really complicated. And it takes a lot of computer programming, but it can be done, and we have parallaxes for a lot of objects. But what that means is that we can't just look at an object once. We have to look at an object at least twice in our orbit around the sun. But it's better the more data points you can get along our orbit to really fill in these line of sight axes here to really help you determine the parallax angle. So that's a lot, but this is how we measure the distances to objects. And so I'm going to give you one little test you can do to really understand what parallax is. So if you're all at home or wherever you are, as long as you're not somewhere that this would embarrass you, but I mean, if you were me, you would do it anyway. So I want you to take your pointer finger and stick it in front of your face, like right in the center of your face, right in front of your nose. And I want you to look at your finger and then close one eye. Now note where your finger is compared to the background behind it. Okay, now open that eye and close the other one. And note now where your finger appears to be compared to the background behind it. And if you just keep switching off which eye is closed, you can see this happening more frequently. And don't worry, I am actually doing this with you right now. And so you see your finger appears to be moving relative to the background, but you and I both know now your finger is not actually moving, and neither is the background. It's an illusion based on where you're viewing from. So when you're viewing from your right eye, that is a distance away from your left eye, and you can imagine that those are our telescopes. And so when Earth is on the right side of the sun, it sees things differently than when it's on the left side of the sun. So this is essentially what is happening with parallax. So now all of the stars that are visible to our naked eye in the night sky, and even the stars ever individually observed with telescopes, are within our galaxy. That may come as a surprise that you look up and you think you might be seeing. How do you know that you're not seeing stars in other galaxies, but they're so far away that you can't even discern an individual galaxy with just your naked eye, at least not here over in New Jersey skies. We can see them through telescopes for sure, but we can't make out individual points of light that are stars. Supernovae have been observed in other galaxies, but these phenomena are capable of such brightness, they can actually entirely outshine all of the light that their galaxy is producing because they get so bright when they explode. Supernova is a dying star or an exploding star. And actually, that is what we're going to talk about next week. So if you want to know more about it, you can tune in next Wednesday. But what I find most interesting about our solar neighborhood is I mentioned this earlier, the ability to see the faintest objects that we can't see even further away in our own galaxy because they're so faint. So we're talking out to about 100 parsecs right now, which is roughly like 300 light years, 326 light years. And the objects, these faint objects that I'm talking about, they're faint because they're low mass, and they're called a brown dwarf. So this is my area of research that I do as an astronomer. I just graduated and did my thesis on it, and so this topic means a lot to me, but I'm still going to try to keep it short for you tonight because I could probably talk about this for hours. And maybe one day we'll do a course on it. I don't know. But a brown dwarf is a substellar object, and it's one that doesn't have enough mass to sustain hydrogen fusion in the core the way that stars do. So what happens is we have a gas cloud, and it's swirling around, and it gravitationally collapses onto its core or its center. Now, when the gas cloud is really massive, we form a star. And actually, I should have looked up this image earlier to share with you, but I totally forgot. And so I'm just going to do it right now because, you know what? I can, because I'm screen sharing. This is a good one. Okay, let's see, can we see that? Yes, we can. Okay, so what we're looking at here is at the top, you can see two size gas clouds, a really large one and a smaller one. As they collapse and they start to swirl, you can see something's forming at the core, and then around the core is the protoplanetary disk. It's the gas and dust that didn't get pulled in to make the central star, and the disk starts to flatten out, and as the gas and dust particles collide with one another, they start to get bigger, and they can accrete material, and they can become planets. So we're looking down here at this line of a star forming in the center, and then in the disk, a planet forming. Now, if the gas cloud that originally created the star was actually smaller, meaning it just had less gas and dust in it, then it can still form in the same way, but it's going to form a brown dwarf instead of a star. It's going to form a much less massive object. And what is missing from this formation diagram here is that brown dwarfs in their little teeny protoplanetary disks can form planets too. So this is what we're talking about here when we say that brown dwarfs are much less massive. This actually comes way in the beginning from their formation. So brown dwarfs, they are around 10 to 75 Jupiter masses. So they're a little bit bigger than Jupiter, and sometimes they're a lot bigger than Jupiter, but they're much less massive than our sun. So if we look at this image here, we're seeing kind of the relative size of our sun versus a low mass star versus a brown dwarf, and then Jupiter, and then the Earth. So we know the Earth is much smaller. Jupiter is a gas giant, and a brown dwarf is also essentially a gas giant, but it's not a gas giant planet. It is not a low mass star. It's its own category. And the name has an interesting origin too. So these objects were theorized to exist back in like the 1960s by astronomer Shiv Kumar, and they were originally called black dwarfs. But a black dwarf is actually, it was already in use, the term. It's a theorized object. It's when a cold white dwarf, a white dwarf that cools down so much that it doesn't emit any radiation anymore, it would be called a black dwarf. And we haven't been able to see these, so it's still just a theorized term, but it was taken already. So then in 1975, astronomer Jill Tarter suggested the term brown dwarf, using brown as an approximate color. And the brown and the black are coming from a classification for dark substellar objects that we can't see very easily. And so actually before brown dwarfs were found, we didn't even know if we would ever be able to see them. And we thought that they might be what constitutes dark matter. So, you know, you're thinking, okay, there's all this dark matter, and that's a whole nother lesson that we're going to do later on in a few weeks in the course. But there's this extra matter missing in the universe, and we can't see what it is. So it must be something dark if we can't see it, hence the term dark matter. And then there's these brown dwarfs that are substellar objects that are smaller than stars, and we know that we can't see, well, at the time, we couldn't see planets, so maybe we couldn't see brown dwarfs either, and there are just so many of them floating around the galaxy that they would make up this extra missing matter. It turns out that's not the case. Then brown dwarfs were discovered, and then we started seeing a lot of them, and now we know, just based off of doing the math for how much missing matter there is and how much matter brown dwarfs make up, that they're not dark matter. But it was really interesting the way that this term came about. So the first confirmed brown dwarf was discovered in 1994 in the Pleiades Open Cluster, and it received the name Teidi-1. So if that sounds familiar to you, this object was discovered in images collected by the IAC on January 6, 1994, using their 80-centimeter telescope at the Teidi Observatory. That should sound familiar because that's who hosts our Canary Islands observatories. The Slooh telescopes over in the Canary Islands are hosted by the IAC. So these brown dwarfs, the first one was found in 1994, but since then we found over 1,800, I think over 2,000 of them. And what's just so interesting is that because they're substellar objects and their masses are 10 to 75 Jupiter masses, and their temperatures range from all the way at the hot end around in like the 3000 Kelvin range down to about 400 Kelvin. Now Jupiter, I think, is around like 200 Kelvin or so. And stars, I mean, gosh, are tens of thousands of Kelvin. So they're relatively cool due to their low mass. And they're not actually brown. They're actually a purple or magenta-ish color. So, but brown came from us just trying to determine a name that represents something that is hard to see, like it's dim. So these objects are the coldest objects between stars and planets before reaching planetary temperatures. Now, if we look at the main sequence, so you might have heard before that our sun is a main sequence star. It's a G star. So this axis at the bottom here is showing the spectral types of the objects, the spectral classification. So I mentioned that O is the hottest objects, and T, actually there's another classification now called Y dwarfs that this is just an older version, and so it's not on here, but all the way down to Y are the coolest objects. And so these are just letter classifications basically saying that there's a bunch of objects that fall around this temperature that they're called G stars or B stars or A stars, etc. And so on the Y-axis here, we're looking at their brightness. So there's this main sequence of stars where, based on their temperature, they're a certain brightness. And that all makes a lot of sense. We actually know a decent amount about stars because they're so bright, there's so many of them, we've been observing them for so long, and they fall nicely onto this main sequence because they fuse hydrogen in their core. So when the stars collapse and the core gets so overly heated, all of these nuclear particles start to interact with each other and hydrogen gets fused. And this sustaining hydrogen fusion keeps the star around the same temperature and mass and brightness for its life until it blows up and dies, and it gets really bright up here, and we're going to talk about this next week, but it becomes a giant or a supergiant and explodes into a supernova, and then you're left with a dim core, which is actually super hot over here in the O and B stars because they're really dense, but they're much less bright over here in the higher magnitude number. So if you've noticed the magnitude system, the higher the number, the dimmer the object actually is. So a negative object is a much brighter object, negative magnitude object. And so then brown dwarfs, which are over here on the lower end of the main sequence, the M, L, T, and what I said were the Y dwarfs, they're very faint because they're not very massive, and they're cool because they're not very massive. But they don't fuse hydrogen in their core. So they don't have that sustaining mass. They actually radiate away a lot of their energy over their lifetime, and they are cooling over their lifetime. So over the millions of years that brown dwarfs exist, they're constantly cooling, and so they float through these spectral types. And so then there's a degeneracy when we study these objects. We could have two brown dwarfs that are both T dwarfs. We'll pick this one here, this pink color here. So if we have two T dwarfs, one of them could be really, really old. It could be billions of years old. It could have started off as a hot M brown dwarf, and it just cooled over those billions of years into a T dwarf. Or it could be a brand new young T dwarf that was just such a super small original gas cloud that made a much tinier brown dwarf than a bigger one. And so now we have an age degeneracy. And now we're into a problem here. And so there's a lot of other ways that we try to study these characteristics. Mostly if a brown dwarf is part of a young nearby moving group. So we see some stars in the night sky that are moving together, and we know their ages. So if a brown dwarf is part of a young nearby moving group, then we can determine its age because that moving group all formed around the same time, which is why it's still moving together through space. Over time, things tend to fall apart and they lose their gravitational pull. They get bounced around by gravitational interactions. So a group of stars that's moving together, they all formed together, and they're relatively young because they're still moving through space together. And then also when a brown dwarf is in a companion situation. So whether this is, well, actually, I mean, the easiest ones to discern are when a brown dwarf is orbiting a star that's around the size of our sun or larger. In that case, we're able to know a lot about the star. We know its mass, we know its age. I said stars are easier. I won't say easy, but they're easier to study because they are bigger and brighter and we know so much about them. And because they sustain their hydrogen fusion, they live nicely on this main sequence for their lifetime. So we see a star like our sun, or not, but I'm just going to use our sun as a reference. We know its brightness, we know its mass, we know its age. Well, if we see a brown dwarf around it, based on the brown dwarf's orbit, we can determine the mass of the brown dwarf. Based on the age of the sun, we can assume the age of the brown dwarf because our formation theories say that a companion should form around the same time unless it was a capture situation where the brown dwarf just got too close to the sun and the sun took it in and kept it. And in that case, of course, yes, we don't know the age of the brown dwarf, but this gives us a chance. It's kind of our own space lab version. So it's a way for us to study these objects in a laboratory setting almost. So in these companion situations, we can have a sun with a brown dwarf around it, two brown dwarfs that are orbiting each other, called a binary system, meaning that the one doesn't just orbit the other, they're both orbiting each other. That's a binary system. And we can actually, like I said earlier, have a brown dwarf with a planet orbiting around it. And we have seen these. So I talked last week, I said about Alpha Centauri, but Proxima Centauri, which is the third star in that triple star system. So Alpha Centauri is a tertiary. There's Alpha Cent A, Alpha Cent B, and then Proxima Cent. And Alpha Cent A and B were discovered around the same time. So they have similar names, but then Proxima Centauri was discovered later, and it's actually a little bit closer. So it's such a wide orbit with the Alpha Cent A and B that it is, Alpha Cent A and B are around, I think, 4.36-ish light years from the sun, but Proxima Cent is only 4.22 light years from the sun. So it's a little bit closer to us. It's an M5.5. So if you're looking at this main sequence here, this red is the M dwarfs, and 5.5 would fall in the middle. So the classifications go M0, M1, M2, 3, 4, 5, 6, 7, 8, 9, L0. And so there's 10 bins per spectral type. So M5.5 is smack dab in the middle. And the interesting thing about that is, I think I've kind of described so far that brown dwarfs they're not stars, they're not planets, they're in the middle. But actually, these lines are pretty fuzzy. So a M dwarf could be a star still or a brown dwarf. It really just depends on the mass of the system, and we're not perfectly clear on exactly what mass constitutes whether an object can sustain hydrogen fusion or not. We have a relative idea, a range, but we don't have a concrete, down to the down to the kilogram answer here. And on the other end of the brown dwarfs and the Y dwarfs, we also don't have a concrete border for what is a really low mass cold brown dwarf or a gas giant planet like Jupiter. And so there's the question, could Jupiter have been a brown dwarf? And the formation theory of the solar system and the mass that Jupiter actually is says no, it is 100% a gas giant planet. But if Jupiter was just a little bit bigger, could it have been a brown dwarf? And I mean, the answer is kind of yes. Just 10 Jupiter masses is a potential brown dwarf. So we're really pushing the limits on what we are confining into this star, brown dwarf, and planet categories. And that does make it a little bit more complicated, but it also makes it way more interesting to be able to overlap instead of having like a quantized category like these spectral types. We really have a nice flow in between each spectral type into the different objects. So these M dwarfs could be stars or brown dwarfs, and they can host planets around them. So Proxima Centauri is an M5.5. It has a surface temperature of about 3,000 Kelvin. It's about 7 times smaller than our sun, and it's only 1.5 times bigger than Jupiter. So it really falls into that brown dwarf category, and it has a planet around it. So it was just recently discovered in the past couple years, that Proxima Centauri b is an Earth-sized planet, and it orbits Proxima Centauri, the star, in the habitable zone. So the habitable zone of a star is the area in orbit around it where liquid water is sustainable. So it's not so far away that it's cold and all the water would be ice, and it's not so close in that it's hot and all the water would be gaseous. So basically, Earth is in the habitable zone, if you guessed. So around Proxima Centauri b, the planet, is in the habitable zone. Now, because Proxima Centauri, the star, is 7 times smaller than our sun, the habitable zone is much closer into the star because the star is smaller and it puts off less heat. So a planet has to be closer in order for that water to be liquid. Now, when a planet is closer to the star, we run into some trouble. So we're going to explore this a little bit more in depth by talking about the TRAPPIST-1 system. It's a really awesome star with about 7 planets around it. I say about because that's what we've discovered so far. 7 planets around the TRAPPIST star. And I mean, this was just discovered, a year ago. Now, I guess it's been about a year. The TRAPPIST system, so the TRAPPIST-1 star is an ultra cool dwarf star. It's an M8, so really, really close to being an L dwarf because the only thing beyond an M8 would be an M9, meaning it's a cooler M dwarf than the Proxima Centauri star, which is an M5.5. So TRAPPIST-1 is a little bit smaller and a little bit cooler. We call it an ultra cool dwarf. It's about 8% the mass of the sun. It's only a little bit larger than Jupiter, but it is about 80 times more massive than Jupiter. So it's not that much bigger, but it is denser. And it has 7 planets around it, and all 7 planets are terrestrial. And some of them are in the habitable zone. So we're looking at this image here. I think I can click on it. There we go, and really enlarge it. Okay, so we're comparing the TRAPPIST-1 system with all 7 planets to our solar system, only the inner solar system though. So if you look at this here, we can compare the orbits, but in a ratio. This entire solar system, the TRAPPIST solar system, fits all the way down into this little tiny area around our sun. This is enlarged 25 times to be able to show you the scale. Because the main star is so much smaller than our sun, that when it formed smaller, the planets formed closer in, and they needed to be closer in order to have this habitable zone, which is shown in green. So the colors here are the red area is too hot, the blue area is too cold, and the green area where the porridge is just the right temperature. So planets E, F, and G are in the habitable zone of the TRAPPIST-1 system. And by enlarging this about 25 times, you can see where these planets kind of relate to our planets in our solar system. So we have Earth and Mars are in our habitable zone, and the H planet of the TRAPPIST system is out just beyond it. So the B and C stars, they get a lot of heat from the sun. So even though the main star is so much smaller and the planets are closer into it, they need to be in order for the liquid water to exist in the habitable zone. But because they're so close, these inner planets of the TRAPPIST system, they get a lot of radiation from the star. And the X-ray and UV radiation from it, the planets B and C may have lost more than 15 Earth oceans worth of water, depending on their initial water content, if they had any. So basically, they might not have retained any water to remain habitable. And a planet orbiting further out obviously would lose much less water, but this is the issue with being so close into your host planet, is that you deal with a lot more of the radiation, the host star. Being this close into the host star, you deal with a lot more radiation from your star. So another issue that arises that I talked about last week with the Proxima Cen and Proxima Cen b planet is tidal locking. All of the TRAPPIST planets are likely tidal locked to their host star, meaning that the same side of the planet is the side that faces the star all the time. I said that in kind of a twisted way, but the way our moon is tidal locked, we always see the same face of the moon. We never see the other side. That's how these planets are. So one side of the planet is constantly getting a ton of radiation from the star, and the other side of the planet never gets any. And so the one side of the planet is going to be really hot, and the other side is going to be really, really cold. So since all of these planets are likely tidal locked, the development of life on any of them is potentially really challenging. The habitable planets, habitable zone planets, are the only ones we really should concern ourselves with in terms of potential habitability, but understanding the way the radiation from the star affects the surfaces of even the outermost and the innermost planets is really interesting, especially because we know in our own solar system that studying moons of planets has been imperative to looking for life in other places. So what about moons of some of these objects? It opens up a whole new field of study. So these tidally locked planets, because you can see here actually what we call the terminator line, where there's a line between the sunshine on one side and the dark on the other. And this is actually potentially the safest place for life to probably live, in this near the terminator line, where it's kind of like the twilight area. So it's not super hot and it's not super cold. But the problem with a tidally locked planet is that because of the way it's only like half being heated, you can get some really severe winds that circle the planet. And so even on the terminator line, you might be hit with some very strong winds at that, because so these strong winds on one hand can do a lot of damage, but on the other hand can do some good because it can help distribute the heat and the cold around the planet, possibly making some areas hospitable in the temperature range that they need to be. So then when a planet is so close to the host star like this, the star is emitting X-rays at a level comparable to our sun, actually. So an M dwarf is a very highly active brown dwarf or low mass star. Because of its size, it's just putting off a ton of solar flares. And we deal with this on the Earth. When our sun emits a really strong solar flare, that's something we have to pay attention to, because we can completely lose our power, for example. So some of the observations of the solar flares on this TRAPPIST-1 host star, the energy of one of the strongest events that they measured was comparable to the Carrington event, which is one of the strongest flares ever seen on the sun. As the planets of the TRAPPIST system orbit so much closer to the star than they do around us around our sun, the eruptions of the solar flares could cause magnetic storms that are like thousands of times stronger than the geomagnetic storms on Earth. That would be some pretty intense aurora borealis, I would think. So I guess if you want to see some, maybe you should go plan your vacation there. We're actually just talking about wanting to go see the Northern Lights one day, and so maybe we should go to the TRAPPIST system. But besides this direct radiation harm that's coming from the solar flares, they can also pose other threats. So the atmosphere of the planet is highly altered by solar flares. And our Earth has our magnetic field, which helps protect our atmosphere, and we're fortunate for that. But we're exploring if there's planets out there that can host life with a lesser magnetic field around it, or even a stronger one. And so there's got to be a perfect ratio where the magnetic field around the planet is adaptable, because the star is going to put off so much radiation, and especially on an M dwarf with a planet so close to it, it's going to be so vulnerable to these solar flares that the magnetic field really needs to protect the planetary atmosphere. Otherwise, on a regular basis, the solar flares are just going to completely chemically alter the atmosphere of the planet, which obviously life won't be able to adapt to on such quick timescales like that. The atmosphere can also be eroded completely. It can be completely blown away. We're talking about solar wind coming off of this host star that would just blow the atmosphere particles off of the planet. A really strong magnetic field could protect the atmosphere, but an Earth-like exoplanet would need a magnetic field that could be hundreds to thousands of times stronger to shield one of these habitable zone planets from the flares that would come from an M dwarf host star. So if we look at a size comparison here, this is Jupiter up at the top and the Galilean moons. Is this coming through? Okay, yeah, I think the resolution's all right. So this is Jupiter and the 4 Galilean moons. So the 4 largest moons of Jupiter that are innermost, and they were the ones that Galileo Galilei observed back in 1610. We have Io, Europa, Ganymede, and Callisto. And these are the relative sizes. Then we have the TRAPPIST-1 host star, and you're looking here at the 7 planets that orbit it in relative size. And then our sun, which you're only seeing a tiny little portion of because it's so big in comparison to the TRAPPIST-1 star and the Jupiter. And here's our inner solar system planets for comparison size. But see how TRAPPIST is so much more similar to a Jupiter-sized object. So when we talk about life around an M dwarf like TRAPPIST, we really should be talking about life on a moon of a gas giant like Jupiter, instead of comparing it to life on Earth around the sun. But of course, you know, that's all the life we know about, so that's where our frame of reference is. But this is why studying moons of gas giants has become such a popular field lately, because it's very similar to studying planets around a brown dwarf, a gaseous brown dwarf. So now I want to just touch quickly before we close up about a question I got in the discussion board. So I'm actually going to pop now to Slooh.com. I hope you don't all see my login. Maybe it kept me. There we go. So if you go to our community discussion boards and go to courses, here's my course. And then I post every week a summary just after the show's over to kind of remind you of what we learned about. You can post questions. This is also where you can find the syllabus and what we're going to learn about next week. The font's kind of small. Sorry about that. But if you go back up, here was a question posted. And this person is asking, sorry, that was an older question. All right, I can't find it this way. So let me just go to, here's another way you can sift through things. Discussions most recent. This is how I usually look through things. But question to page, this is about tonight. Awesome. So the question is that when we're observing and estimating the age of an M dwarf with a potential life-hosting planet around it, if life exists, you know, what are the ages of these M dwarfs? Are we talking about life in the form of bacteria or like single-celled organisms? Are we talking about dinosaurs? Are we talking about our human life and iPhones? And that's a really great question. When we look for life on other planets, what exactly are we looking for? And to be completely transparent with you, we're not looking for aliens. We are looking for chemical abundances in the atmospheres of these objects, of these planets. So when we look at a planet, it is so far away and it is so dim that we can't see the surface of it. We only see the atmosphere, the light that is coming from the very outermost area. So when we only get to see the atmosphere, you're not going to see people waving to you, you know, the way you do. I'm going back to this cruise ship reference when the boat drives by and you see people waving and wave back. That's not what's happening here. We're seeing the atmosphere. So pretend that you were an alien on a spaceship and you drove around the solar system and you're like, oh, look, here's a planet. You know, I wonder if there's life on the surface, but I can't see the surface. All I see is the atmosphere. What are you going to look for? You're going to look for chemical abundances that indicate that there might be life below. So one of the easiest ways for us to do that was to say, what's in our atmosphere that indicates that there's life below it? We know we need oxygen, so we're looking for oxygen in the atmosphere. Now, this is, of course, assuming life like our own, whether from bacteria to dinosaurs to iPhones. So I think it's funny the way we're referring to iPhones here as if they kind of are living, which if we get into the AI discussion, you never know. But so these chemical abundances, you know, we're assuming that we're looking for life that's like our own, and so we need oxygen, etc. But an indicator, one of the interesting indicators is methane. There's a certain amount of methane that is produced from life living below the atmosphere, and so if we can find that abundance of methane on a planet, it could indicate that there is oxygen breathing life down below. But when we are looking out at these atmospheres trying to find life, and do we have a really young object? What would that mean for life? Do we have a really old object? Would life still be around? On the young object, did life even form? And on the old object, is life gone? This, I think is a really cool depiction of this. So this is our Earth is 4.6 billion years old. Our solar system is 4.6 billion years old. And so Earth formed just a couple 100 million years after the sun. So we really just round it all to the same 4.5 billion years. If we put this 4.6 billion years into 1 hour on the clock. So Earth's crust finally forms at minute 1. The inferred origin of life, so this is inferred because we don't know for sure, obviously we weren't there, is almost at 10 minutes. It's at 9 minutes later. And that seems quick, but given that this entire hour is 4.5 billion years, you can divide this number by 12. So if we then look around, we have the first bacteria not coming in until minute 17. And so from there, we're forming cells, we have a jellyfish, we have land plants, insects, amphibians, reptiles, dinosaurs at 57 minutes. So from Earth forming, it took 57 minutes out of the 1 hour, out of the 60 minutes for the first dinosaur to form. The first modern human, so us, well, not even us really, but our ancestors, the first modern human didn't form until the last possible second of that hour. So if you put all of Earth's history, all 4.6 billion years of Earth's history into 1 hour, humans are the last second of that hour. So if you want to know, when we look at a potential brown dwarf system with planets around it that could host life, and is the brown dwarf a couple 100 million years old? Because then it's young. And if it's young, probably nothing even got the chance to form yet. And if it's really, really old, like 4.5 billion years, then maybe we might be able to start assuming there could potentially be an alien of some sort. And if it's double this age, if it's nearing the age of the entire universe, if it's nearing 13 billion years old, then the chances of life still being around, unless they were super successful, are probably pretty slim. So the problem, aside from all of the actual physical problems of life forming around objects like these at all, the problem of us trying to find it is also 1 in a million. Or, I mean, that's not a real statistic, that I just made that up, but very, very minimal, considering we were just the last second in our 1 hour on Earth. So I'll let you digest this as we close for the night and just think about really where this puts you on Earth. We are referred to as the pale blue dot, the little speck. It makes me think of, what's that? The Who's on the little dust grain. But it's true. And to know that we are on this little speck floating through all of space, and we've only just arrived a second ago in the hour of Earth's history. It's a really deep thought, and I'm going to leave your Wednesday off with that. So that's all I've got for tonight. If you want to join me next week, same time, same place, Wednesday, 7:30 p.m. Eastern Time, we're going to talk about stellar evolution from the birth of stars all the way to their fiery, explosive deaths. It sounds morbid, but it makes for some beautiful pictures, and we're really going to look through those on Slooh.com next week. So I hope you join me. We'll see some beautiful images, and we'll talk about all about the stellar evolution. Have a great night. Clear skies.